Welcome to the last video in the series for Unit 2, Topic 2.6, Adaptations. As we've learned previously and seen countless examples of, the features and conditions of an environment have a direct influence on what kinds of organisms are capable of surviving within it. The abiotic resources, climate patterns, light availability, seasonal variation, and even the topography of a habitat are all responsible for the evolutionary development of the structural, or anatomical, and functional, or physiological, traits possessed by organisms that allow them to survive there. But also, as we've previously seen, constantly changing environmental conditions lead to a constantly changing biodiversity of an ecosystem. The simplest definition of a population states that it is a group of individual organisms all belonging to the same species. All of the zebras coexisting together, this school of salmon, and this portion of a Douglas tree forest all represent examples of a population. If we were to look more closely at one of those examples, or any other population, because they're the same species, we would find that they are anatomically and physiologically extremely similar to one another. They would all have the same anatomical structures and internal organs, and would function in the same way. But if we were to look more closely, with more attention to detail, at each of the individuals within a population, we would begin to recognize slight differences between those individuals. The exact pattern of stripes on the zebras might vary ever so slightly. In the salmon, fat content that's providing the energy for them to swim upstream to their breeding ground might differ somewhat. The density of the needles on the branches of Douglas fir trees is likely not uniform. These differences could hypothetically be measured, and we would observe that most individuals in a population are average in their variations, and very few individuals would have extreme variations. And why do these anatomical and physiological variations exist in a population? They're thanks to the genetic information that is passed down to offspring from their biological parents. Any given individual in a population of flamingos, snails, or humans will have variations in their characteristics that reflect those found in their parents. With the exception of mutations that organisms accumulate throughout their life, the genetic information an individual has doesn't change as it ages. Actually, even those mutations don't fundamentally change an organism's anatomical characteristics or its physiological functions. This means that individuals are largely incapable of changing their very nature if and when environmental conditions change. However, one of the basic tenets of evolutionary theory states that populations, over long periods of time, change in response to environmental conditions. It is, in fact, changing environmental conditions that select for or against individuals based on their unique variations. So, although we wouldn't describe an individual as adapting to environmental change because it's incapable of doing so, we can say that populations adapt to their environment. There is one important note to make about this, and that is, if the environmental change is occurring quickly, there simply may not be enough time for a population to evolve and meet the new demand of its environment. But if changes are slow enough, and there is enough genetic and phenotypic variation in the population to begin with, characteristics that improve survival will become more common in a population, and those that make survival more difficult will become less common, perhaps disappearing altogether. An adaptation is a characteristic of a species, either anatomical or physiological, that makes it possible for that species to survive in a particular habitat. A species' characteristic adaptations are key in allowing them to occupy their ecological niche. It is a species' environment and the conditions within it that drive the evolutionary change that results in those adaptations. The availability of light and water are influential on plant adaptations. Cacti, found in arid environments, have adaptations allowing them to both store and protect, with sharp spines, the water they have. Most plants grow in soil and have leaves containing stomata for gas exchange on the bottom surface of them, but water lilies have roots that are adapted to grow in water as they dangle beneath the pads. The pads themselves have stomata on the top surface, since the bottom surface is underwater. In a steep, treacherous place like this, a mountain goat's extra wide hooves and the rough pads on the bottoms of their toes allow them to traverse their environment sure-footedly. Carnivorous plants, like the Venus flytrap, have adapted to survive in places with nutrient-poor soil. They supplement what the soil isn't providing by consuming small insects. Consumers have a wide variety of adaptations, allowing them to access the food sources that are available in their habitat. Hummingbirds' long tongues means that it has the access to the nectar deep inside a flower. An herbivore has wide, flat teeth useful for crushing and chewing vegetation. Carnivores have sharp, piercing teeth so it can cut and tear through flesh. Some plants don't shed their needles or leaves in the fall and winter, allowing them to photosynthesize all year round. A polar bear can provide a bunch of examples of adaptations. The teeth of a carnivore for its diet, its white fur coat for camouflage as a predator and for survival in a cold environment, a layer of blubber beneath its skin, which also helps to retain heat in its cold, harsh environment, forward-facing eyes, allowing it to effectively gauge the distance between itself and its prey. Large paws help to distribute its massive weight on thin ice. Even infectious diseases have driven the evolution of organisms. Because resistance to a disease varies within individuals of a population, exposure of a population to a virus like Ebola, influenza, or tobacco mosaic virus puts susceptible individuals at risk. Those that do survive an outbreak can pass on the genetic information that granted them resistance to their offspring. Of course, it is important to note that in the case of infectious viruses, that viruses evolve as well. When an environmental change takes place too quickly or is catastrophic, like an asteroid impact, massive volcanic eruption, or widespread plague, populations may not be granted the time necessary to adapt to that change. Additionally, if that population didn't have much genetic variation to begin with, that can add on an extra layer of difficulty. A population may end up altering its behaviors. Scientists have noted that a number of bear species are beginning their hibernation cycle an average of 6 days later, since fall and winter are increasingly more mild due to climate change. Peregrine falcons have adapted quite well to city living, making their nests in the ledges and overhangs that many skyscrapers have. Populations might also have to migrate in search of more suitable habitats. As there is less and less Arctic sea ice to hunt from, polar bears are migrating farther south in search of food. The city of Lopburi in Thailand was overrun by monkeys, shown here in June of 2020, as the city encroaches on their forest habitat and they search for food. But if altering behaviors or migration aren't feasible or possible, a third outcome exists: extinction. In the last 550 million years, there have been 5 major extinction events, including the one at the end of the Cretaceous that wiped out the dinosaurs. But even outside of those dramatic mass extinction events, it is estimated that 99% of all species that have ever existed have gone extinct. Actually, extinction is the ultimate fate of all species. And on that cheery note, that concludes our look at Topic 2.6 and Unit 2. Thank you so much for watching. Take care.